Besides the various gravitational effects that we've been discussing, the single most important perturbation effect for orbits around planetary bodies is due to atmospheric drag, otherwise known as gas drag. Here we're going to develop a basic model of atmospheric drag, but keep in mind that it is possible to create much more complex models, and also to increase the fidelity of this particular model in various different ways, which we will discuss shortly after writing down the basic formalism. We have a planetary body with some kind of atmosphere. Our spacecraft P is located within the atmosphere somewhere. We have an inertial frame that's fixed to the center of the body, but not rotating with the body, and a non-inertial frame, which we've previously called G sub B, that is rotating with the body. The drag force on the spacecraft due to the atmosphere is given by -1/2 times the drag coefficient, which is determined by the shape of the body, the cross-sectional area, so the area presented by the body to the atmosphere that it's in, the atmospheric density, and we'll have a lot more to say about how we model atmospheric density later, all this times the square of the relative velocity of the spacecraft to the atmosphere in the direction of that relative velocity. The relative velocity is the inertial velocity of the spacecraft with respect to the center of that central body minus the inertial velocity of the atmosphere with respect to the center of that central body. We apply the transport equation, and we can write this inertial velocity of the atmosphere as the rotating frame velocity of the atmosphere with respect to the center of the central body, plus the angular velocity of the non-inertial frame and the inertial frame crossed with the position vector of the spacecraft. In the case where the atmosphere is just moving along with the rotation of the body, this is the no wind case, where the entirety of the atmosphere is just rotating at the exact same rate as the body, this body frame derivative is going to be 0. And so this is the model that we're going to adopt. And this is vastly simplified because, of course, in real planetary atmospheres, there are winds. The entirety of our atmosphere does not move as one block along with the rotation of the Earth. But for a first cut, this is a reasonable approximation. So at the end of the day, we will write the relative velocity is approximated by the inertial velocity of the spacecraft minus the angular velocity of the planet crossed with the position of the spacecraft. And we're using the position of the spacecraft here because it's assumed that the spacecraft is in the atmosphere. And so the location of the spacecraft also describes the location of the particular chunk of atmosphere surrounding the spacecraft at any given point in time. We frequently define something known as the ballistic coefficient, which is the ratio of the spacecraft mass to its drag coefficient scaled by its cross-sectional area. And for simplicity, we frequently take the cross-sectional area to be a constant. So we ignore the fact that the spacecraft might be changing its orientation within the atmosphere with respect to its velocity vector, and therefore that the cross-sectional area might be changing somewhat in time. To this sketch, we can add the position of the spacecraft, and we can add our rotating frame. So the ER direction, as usual, is the radial direction, and E theta is the orthogonal direction in the plane of the spacecraft's orbit. This angle is the true anomaly. And for some spacecraft velocity, V, we have previously defined the flight path angle phi FPA. We are first going to consider the effects of gas drag on a nearly circular orbit. To make the equations a bit simpler, we are going to define a parameter B that is 1/2 the drag coefficient times the cross-sectional area. And as we're dealing with a nearly circular orbit, we can approximate the orbital radius as the semi-major axis times 1 minus the eccentricity times the cosine of nt, where n is the mean motion and t is time. Therefore, the radial force on the spacecraft, F sub r, is given by the magnitude of the drag force times the sine of the flight path angle, and is equal to negative this b factor times the atmospheric density times the relative velocity magnitude times the gravitational parameter of the central body divided by the specific angular momentum of the orbit times the orbital eccentricity times sine of the true anomaly. And similarly, the component of drag force in the orthogonal direction is given by the drag force magnitude times the cosine of the flight path angle, and is equal to negative b rho v rel mu over h times the quantity 1 plus E cosine of nu. We can now apply Gauss's equations, which tell us the time derivative of the eccentricity is equal to the radial component of the perturbing force times h over mu sine nu plus f sub theta times the quantity 2h over mu cosine nu plus r times vr. This is the radial component of the velocity over mu sine nu. The radial component of the velocity we have previously established is mu over h e sine of nu. And r we can always write as h squared over mu over 1 plus e cosine of nu. And in the case where the eccentricity is small, we can approximate to first order the true anomaly as nt plus 2e sine of nt. And that means that we can approximate the cosine of nu as, and therefore the velocity magnitude can be approximated as the square root of mu over a times the quantity 1 plus e cosine of nt. We take all this, we put it back into our E dot expression, and we approximate dE dt is negative 2b rho square root of mu over a times the quantity cosine of nt minus the eccentricity plus 3 times e cosine squared of nt. So remember, this is for small eccentricities. This is for already nearly circular orbits. But what we find is a strictly decreasing eccentricity. And so what the basic finding is, and what the basic finding will always be regardless of your model, as long as your model is at all descriptive of what the atmosphere actually does, is that drag circularizes the orbit. Initially, this effect is very, very small because the density is very, very low at high orbits. But as your spacecraft comes down and the density ramps up, this accelerates, and eventually you kind of fall off a cliff and your spacecraft just goes plunging down into the atmosphere. For Earth, we typically consider this to be at around the 200-kilometer level or so, when drag effects are completely dominant over everything else and your orbit starts to shrink very rapidly. We can do the same thing for the semi-major axis. The change in semi-major axis is equal to 2h h dot over mu times 1 minus e squared plus twice a e dot over 1 minus e squared. H dot is going to be given by the orbital radius times the tangential component of the perturbing force. And we've already written out the expression for E dot. So when we put everything together, we will get an expression for A dot that looks like, that is, the rate of change of the semi-major axis is given by the quantity 2hr over mu times 1 minus e squared plus 4aeh over mu times 1 minus e squared times cosine of nu plus 2aer v sub r, that is the radial component of the velocity, over mu times 1 minus e squared times the sine of nu, all times the tangential component of the perturbing force f sub theta, plus 2aeh over mu times 1 minus e squared sine of nu times the radial component of the perturbing force f sub r. Once again, we will make the approximation that the eccentricity is small, and in this case, we can rewrite this expression scaling by the original semi-major axis, so A dot over A, as approximately 2h over mu times the quantity 1 plus e cosine of nu plus e sine squared of nu times f sub theta plus 2h over mu times e times sine of nu times f sub r. If we plug in the particular values of f sub theta and f sub r for gas drag, we find that in this case, A dot over A is approximately negative 2b rho A times the mean motion n, all times 1 plus 3e cosine nu plus e sine squared nu. And as expected, what we found is that the semi-major axis is also decreasing in time. And again, mediated very much by what the magnitude of rho is. So just as with the eccentricity, the effect is small when you're high up and then rapidly accelerates as you drop lower into the atmosphere. And therefore, increases the rate at which your semi-major axis shrinks. We did a lot of kind of haphazard approximations to get these results, and they have relatively good predictive power, but only as averages and only as in the general sense of what's happening. You can build much more complex atmospheric models, and many of these exist, but because measuring what the actual atmosphere is doing is so difficult, even the most powerful mathematical models are completely reliant on how well you can actually estimate all of the involved quantities, and in particular, what the local atmospheric density is actually doing. And for this reason, it's incredibly difficult to predict exactly where a spacecraft is going to be if it's interacting with an atmosphere. And so for many spacecraft, it's not worthwhile to make these predictions if you really need to have completely accurate knowledge of where the spacecraft is in Earth orbit. Then you equip it with GPS radios and use the GPS constellation to exactly pinpoint it. You obviously can't do this for things that aren't already equipped with the proper equipment, or for things that are dead, like old satellites or rocket bodies that were launched up and are now tumbling down. And so a lot of effort is expended all the time to track these things and to try to predict them out. But the predictions are very short term, and the inaccuracies grow incredibly when you're talking about many orbits worth of data. This is why frequently in the news, you will hear about something like a rocket body, for example, coming down, and there being a lot of uncertainty as to where exactly it will hit. Fortunately, the Earth is mostly water, and so the vast majority of the time, the answer is these things will fall into the ocean. We're going to take a quick look at one of these more complex models, but not derive it because it uses many of the same exact tools that we have already brought to bear. And so the derivation is not as interesting as the basic results. So here we have a model for secular perturbations due to atmospheric drag that tracks very closely to the description in Volato, which itself is citing a 1987 paper by King-Healy that results from a power series expansion of the term eccentricity times the cosine of the eccentric anomaly. And as we've previously seen with such expansions, this results in a series in the modified Bessel functions of the first kind, which here we're calling I sub s, so as not to confuse with the j's that we've previously used. This model makes a prediction for the change in semi-major axis per revolution. So this is an absolute change in semi-major axis. This is not given as a rate, but you can always turn this into a rate or convert back and forth between this and a dot with knowledge of what the current orbital period looks like. And what it says is that the change in semi-major axis over the course of one revolution, on average, due to atmospheric drag perturbations, is given by -2 pi times this quantity q squared, where q is 1 minus the planet's rotation rate times 1 minus the orbital eccentricity to the 3/2, over the orbital mean motion times the square root of 1 plus e times the cosine of the orbit's inclination, times the cross-sectional spacecraft area times the drag coefficient over the spacecraft mass. So you might notice the reciprocal of the ballistic coefficient in here, times the semi-major axis squared times the density at periapsis, and then times this series term in these modified Bessel functions of the first kind. And all of these, this I naught, I1, I2, and I sub 3, have their argument of z, which is a times e over the atmospheric scale height. And we're going to come back to this term in a little bit. So we have the 0th order Bessel function times 2e times the first order Bessel function plus 3e squared over 4 times I naught plus I2 plus e cubed over 4 times 3i1 plus I3 times the exponential of negative of the z term, which again is ae over the atmospheric scale height. We have a very, very similar expression for the change in eccentricity per revolution, and I'm not going to read it out, but you can see that the forms are quite similar with just small differences in this Bessel function expansion. We can write equivalent expressions for the change in the inclination, the change in the longitude of the ascending node, and the change in the argument of periapsis. And we see here that atmospheric drag really affects everything. It has an effect on essentially all of the orbital elements. And furthermore, there's going to be coupling between these effects. The changes in the various angles are going to drive one another, and the changes in the semi-major axis and eccentricity, because they keep dropping you down and they keep changing and growing the density of periapsis, are going to have an effect on all of this. So all of these are accelerating processes.